Now, in addition to CFCs, there's a number of other ozone depleting substances that were being produced during this same time period and thus subsequently emitted on a large scale. And the first of those is a class known as hydrochlorofluorocarbons, or HCFCs. These have a general structure such as shown here. It's essentially very similar to CFCs, it's just that the molecule contains a carbon-hydrogen bond. Now, during the late 1980s and into the 1990s, when CFCs had been restricted by some regulation, as we'll talk about in a few minutes, these HCFCs came out as companies scrambled to find replacements for CFCs. So these were used as a temporary replacement for CFCs in the 1990s. And the reason that they're used as a replacement is because HCFCs do have a tropospheric sink. So if we react this prototypical example here, chlorodifluoromethane with hydroxyl radical, the CH bond can be cleaved, so you can get a hydrogen atom abstraction by the hydroxyl radical to form water and leave you with a chlorodifluoromethyl radical here. And this reaction is downhill in energy. It's exothermic by close to 80 kilojoules per mole. And so after this reaction, we've produced a radical on this intermediate here, which can react with diatomic oxygen in the air to then undergo subsequent oxidation reactions and removal from the troposphere and removal from the atmosphere. Now, we can look at this reaction here not only in using heat of formation data to calculate the overall enthalpy of reaction as I've done, but also just by comparing some bond strengths. So on the left side here, the CH bond is about 421 kilojoules per mole, whereas the OH bond is stronger, close to 500 kilojoules per mole. And so this reaction should be favorable. We're going from a weaker bond to a stronger bond, so that's a favorable process. Now, not all of the HCFC will be removed via the tropospheric sink. There's always going to be some fraction that escapes into the stratosphere. And in this case, that could be about maybe 5% of the HCFC will escape the tropospheric sink and rise into the stratosphere. And what occurs in the stratosphere is very similar to CFCs. We'll have absorption of UVC light and then dissociation of the carbon-chlorine bond to produce a free chlorine atom that can then go on to participate in ozone destruction. So at the end of the day, HCFCs really aren't a good alternative to CFCs. They're certainly better, but they're not a final alternative. If we produced HCFCs on the same scale as CFCs were being produced on, we would eventually continue to increase the level of chlorine concentration in the stratosphere. Another important class of ozone depleting substances is known as halons. Halons are defined simply as being bromine containing hydrogen-free compounds. So they're essentially CFCs, just where we've replaced one of the fluorine atoms with a bromine. Now they can contain only bromine and fluorine, or it can contain bromine, chlorine, and fluorine. And these compounds are used extensively, or were used extensively in firefighting. They're very effective firefighting agents that unfortunately don't have any tropospheric sink. If we make a similar comparison as previously, in this case looking at abstraction of that bromine atom, unfortunately we see that this reaction is uphill by about 80 kilojoules per mole, so it essentially does not occur on a relevant time scale for this to be a tropospheric sink. We can make this same comparison just looking at bond strengths. The CBr bond is stronger than the BRO bond, and thus it's the reaction in the forward direction is unfavorable. It's uphill or endothermic. We're going from a stronger bond to a weaker bond, which is not favorable. And the thing about halons is that they will undergo dissociation in the stratosphere to produce free bromine atoms that then go on to destroy ozone on, in some cases, a massive scale, Bromine, as you'll remember, is more active than chlorine generally because it exists primarily most of the time in its active form and not in its inactive form like chlorine. One other example of chlorine or ozone depleting substances is just chlorocarbons. Any molecule that contains a carbon-chlorine bond. A couple specific examples here. Carbon tetrachloride is probably the most potent example. This does not have a tropospheric sink. This methyl chloroform, the other example here, does have a tropospheric sink because of the CH bonds, which can be abstracted by hydroxyl radical. But still, this is also an ozone depleting substance. These were used extensively as dry cleaning solvents or metal cleaning solvents during the 60s and 70s, but now have started to be phased out. And that kind of leads us into our next discussion. So if all of these agents were being produced and produced on a massive scale during this time, and what happened? We certainly saw this increase in chlorine concentration in the stratosphere, resulting in the production of the ozone hole. But how have we started to repair that? And that comes from some national and international agreements that have been put in place to limit the production and thus emissions of ozone depleting substances. So I have a short timeline here to give you a quick snapshot of what was going on during this time. Certainly, there are other things that are not on this timeline, but I've just highlighted a few. So 1957, that was the beginning of the British Antarctic Survey's measurement of ozone concentration, of overhead ozone concentration. And there were certainly things occurring during the 1960s in regards to atmospheric regulation. But it was really a 1974 paper by Mario Molina and Sherwin Rowland that described ozone destruction by Cfcs specifically. And this paper really set off the alarm bells and got a bunch of both national and international conferences going. And in 1978, this actually resulted in the US banning non-essential CFCs in aerosol cans. And the US was joined in this by Canada and Sweden and Norway as well in 1978. And there was additional conversation and meetings and regulation that were starting to be drafted in the early 1980s. But it was really a Vienna Convention in 1985 where about 43 different countries came together and made this non-binding agreement where they simply all agreed to begin looking into taking the necessary steps to limit ozone depletion. And now in 1985, this led then to the finally led to the 1987, I apologize for the slight error there, but the 1987 Montreal Protocol. This was now a binding agreement that was signed by 60 nations. That number is now up to 197 and was facilitated by the United Nations. So this is really a worldwide agreement, a binding agreement to limit and remove and phase out production of CFCs and other ozone depleting agents from production and regulate emissions very heavily here. And this has been followed up by subsequent regulation up through the 1990s and 2000s. Now, the results from this is that after the 1970s and particularly in the 1980s, we see a drop in the overall production of these CFCs. So if I look at just CFC 11 and CFC 12 in this diagram we've shown earlier, we see that up until about the 1970s, we saw a large dramatic increase in these. And then in the 1970s, the US and a couple other countries started to really back off their production of CFCs through some regulation. And then as the US backed off their production, the rest of the world that didn't have some of these regulations actually increased their production of CFCs in order to meet the demand, kind of to offset some of the demand by the UFC's decrease. and in production. So we see kind of this rise again in the early 1980s. But then when the Montreal Protocol was put in place, then we saw essentially just a dramatic drop in all emissions worldwide and production of CFCs. And so by about 2000, we've got a very low production and emission of CFCs worldwide. Now, this dramatic drop in production and thus emissions of CFCs isn't exactly mirrored by a similar decrease in stratospheric concentration of CFCs. And this is where we need to talk about lifetime of CFCs and other ozone depleting agents in the stratosphere. So a couple examples here, just CFC 11 and CFC 12, their lifetime or their concentrations illustrated in the stratosphere. So certainly we have this increase in concentration up until about 1987 that mirrors just kind of the natural production of CFCs throughout the world. But then after 1987, we start to see a slight decrease. Really, actually, we peaked in concentration in the stratosphere around 2000 because it takes time for some of these emissions to rise through the troposphere and up into the stratosphere and into the upper stratosphere. But then we see this really slow decline, and that's because there's no tropospheric sink, as we mentioned, but there's no really stratospheric sink. There's a really slow process for cleavage and removal of the CFCs from the stratosphere. And so the stratospheric lifetime for some of these molecules is on the order of decades. And so what we'll see overall then is the ozone hole, even though we have dramatically decreased the production of many ozone depleting substances, the ozone hole is predicted to be around until maybe the mid 21st century or later, simply because it's going to take a long time for the concentration of chlorine in the stratosphere that's directly tied to the concentration of these CFC, HCFC, and other ozone depleting substances, that the free chlorine concentration is tied to the concentration of those substances. And because it's a long process for those to be phased slowly out of the stratosphere, we will continue to see active chlorine production and ozone destruction on a massive scale, and thus the production or the phenomenon of the ozone hole until probably about the mid-21st century. Okay, so that's a lot of discussion, but where have we moved away from CFCs? We still need refrigerators, we still need air conditioning, we still need firefighting equipment. So how have we changed production in order to be able to meet that need? And the main CFC replacement has come to be HFCs, or hydrofluorocarbons. These are a few examples simply shown here. They look a lot like CFCs, just they don't have the chlorine atom, and they all have carbon-hydrogen bonds. The advantage to that is that they do have a tropospheric sink. Now, these compounds have somewhat similar thermal properties to CFCs, and so they're used in refrigerators and air conditioning, and somewhat in fire suppression as well, since they have somewhat similar properties to halons. But now they've got that tropospheric sink because of the carbon-hydrogen bond. So abstraction of that CH bond there is downhill, it's exothermic. And then the resulting radical here can be oxidized through reaction with diatomic oxygen, or O2, and thus removed from the troposphere. But the other advantage is, even if some of this rises up into the stratosphere, which some of it will, it's less of a concern on the ozone destroying side, because fluorine atoms, if they're produced via photolysis, is rapidly deactivated as HF, and thus does not exist really as an active catalytic ozone destroying agent. Now, why is HF so resistant to being activated? Well, it turns out that the bond strength for HF is 565 kilojoules per mole. It's one of the strongest bonds, and thus activation of HF by reaction or abstraction of that hydrogen atom by hydroxyl radical or nitric oxide or any other species that exists in the stratosphere is almost guaranteed to be endothermic, simply because all of those resulting bonds are going to be weaker than the HF bond. Now, as we'll talk about in some of the later chapters, HFCs don't come without their disadvantages. They turn out to be fairly potent greenhouse gases, which makes them really not desirable, and they are regulated to some degree, but at least in terms of ozone destruction, they are much less of a concern, and these are primarily used in refrigeration nowadays.